Have you ever really thought about how your car manages to do so much at once? I mean, it's making life or death calculations 1 millisecond and seamlessly playing your favorite song the next. Well, today we're going to pop the hood and take a look at the two completely separate brains that make your smart car, well, smart. Okay, so here's a question for you. What could your car's airbags and its music player possibly have in common? I know, it sounds kind of weird, right? But the answer actually gets to the very heart of a deep, fundamental split in how your car's computers work, a division of labor that separates the absolutely critical from the merely convenient. You see, they both run on computers, sure, but they are playing by completely different rulebooks. On one side, you have a system that is all about life or death split-second timing. The other? Well, let's just say it can afford to be a little late to the party. And that's because they're designed to solve two fundamentally different problems. So how in the world do you solve these two opposite problems in the same vehicle? Well, you don't use one brain. You use two. Your car has what's called a real-time operating system for all the critical stuff, and then a general-purpose operating system for, everything else. Just look at the primary goal here. The airbag's brain, the RTOS, is absolutely obsessed with something called determinism. Now, that's just a fancy word for one simple thing. You can never, ever, ever miss a deadline. But the music brain, the GPOS, it just cares about throughput. It's a master multitasker trying to keep all your apps running pretty smoothly, not really worrying if one is a millisecond late. And this quote just hits the nail on the head. For that airbag system, being late is the failure. That's it. Game over. There's no coming back from that. For your music player, a failure is just an app crashing. Yeah, it's annoying, but you just restart it. So you see, one system defines success as being perfectly on time, and the other defines it as just being generally productive. And get this, these different brains aren't just running different software. Nope. They actually run on completely different types of processors. We're talking hardware that is designed from the ground up for its specific job. So on one side, you've got the Cortex-M processor. This is your specialist, built for real-time control. Think of it like a surgeon's scalpel. Incredibly precise, efficient. On the other side, you've got the Cortex-A. That's the powerhouse, designed to run complex apps. That's your Swiss Army knife. And the huge difference between them, it really all comes down to one tiny critical piece of hardware. And that piece of hardware is the MMU, the Memory Management Unit. This little guy is what makes it all possible. It enables this incredible concept called virtual memory, which basically gives your infotainment system superpowers, like the ability to run a dozen apps at once without them ever crashing into each other. So, how does this MMU actually work? How does it protect your music app from, say, crashing your navigation right when you need it most? Well, it's all thanks to this incredibly clever concept called virtual memory. So here's the fundamental problem that virtual memory solves. If every single app could see and access all of the computer's memory, while one buggy app could accidentally scribble over another app's data, that would cause a catastrophic domino effect, bringing the whole system down. Total chaos. The solution, honestly, is brilliant. Think of your car's physical memory, the actual RAM chips, as a city full of houses with real street addresses. Now, instead of giving those real addresses to every single app, the operating system gives each one its own private set of P.O. boxes. So here's what happens. Your music app asks to access its P.O. box number 100. The MMU acts like the postmaster. It looks at the request, goes to a secret map, and translates that P.O. box number into the real physical address, 123 Main Street. Now, your navigation app might also think it has a P.O. box number 100, but the MMU translates that to a totally different physical spot. The apps have no idea what the real addresses are, which creates this perfect, secure wall between them. And that segmentation fault, that dreaded error that programmers see all the time, well, all it is really is the system's way of saying access denied. It's just an app trying to peek into a P.O. box that doesn't belong to it, and the operating system shuts it down on the spot to protect everybody else. Okay, so that's how the system keeps everything running safely and separately. But how does it all start in the first place? Let's take a look at the boot process, this super complex sequence of events that happens from the moment you turn the key. You should think of it like a multi-stage rocket launch. The first stage, the boot ROM, is this tiny, unchangeable program that's literally burned into the chip. Its only job is to light the fuse on the second stage, the bootloader.
The bootloader then wakes up all the critical hardware, loads the main operating system, the kernel, into memory, and then passes the baton. And finally, the kernel takes over, firing up all the services that bring your infotainment screen to life.
And this whole process brings us to a really, really clever innovation, the device tree. Think of it like a universal instruction manual that describes the hardware. See, in the past, you'd need a custom version of the operating system for every single car model. But now, you can use the exact same OS on tons of different hardware designs just by giving it a different device tree file at startup. It is an absolute game changer for efficiency. All right, let's zoom in even further. Let's go from the whole system level all the way down to a single line of code. Because in the world of these critical real-time systems, one single keyword can be the difference between a working airbag and a complete system failure. And that keyword is volatile. It's a command, a direct order to the compiler that basically says, hey, listen up. The value of this thing can change at any random moment because of something happening in the real world. For the airbag, you have to read the crash sensor's value right now, not a copy you saved 5 milliseconds ago. Volatile makes sure that happens. So here's what's going on under the hood. Normally, a compiler tries to be clever to save time. It might think, hey, I just read that sensor value a second ago, I'll just reuse it. That's what you see on the left. But when you add the volatile keyword on the right, you're forcing it to be obedient. It's a direct command. Don't get cute. Don't reuse anything. Go fetch the absolute latest value from the hardware every single time.
So pretty much all the processors we've talked about are based on designs from big companies like ARM. But what if the blueprint for a computer chip itself was open source? Well, a new approach called RISC-V is making that a reality, and it's changing everything.
This is RISC-V, and its core idea is, well, it's revolutionary. The fundamental blueprint for how a computer chip works should be free and open for anyone to use and customize. And the design is totally modular, like building with Legos. You start with a really simple base, and then you just snap on the specialized blocks you need for your specific job.
And this is the incredible result. Before, you had to pick from this limited menu of expensive, one-size-fits-all processors. But with RISC-V, innovators can now build the exact, perfect processor for any task they can dream up, from a simple smart toaster to a complex medical device. And they can do it without paying a dime in licensing fees. It's just a massive shift in who gets to innovate. So we've gone on quite a journey, right? From the two separate brains in your car to the virtual walls that keep them safe, all the way down to the very language that controls them. We've seen how all these layers of specialization make our world work. And the question RISC-V leaves us with is this: what happens to innovation when the power to create these specialized brains is put into everyone's hands?